do the sample final I gave you. So it says find the equation of the line tangent to this curve. So the equation of the tangent line at some point A is f prime at A times x minus A plus f of A. We're supposed to do it at the point 1, 2, so A will be 1, and f of A, f of 1, will be 2. So all we need is the slope. We get that from the derivative, so let's take the derivative of this. The derivative of x to the third is 3x squared. Derivative of minus 3x squared is minus 6x. And the derivative of 4 is 0. If I put 1 into this, I get 3 minus 6, which is minus 3. So the equation on the tangent line will be negative 3 times x minus 1 plus f of 1, which is 2. That's number 1. Number 2. So now we have Galileo is reported to have dropped 2 iron balls from the upper balcony of the Leaning Tower of Pisa, approximately 144 feet above the ground. If we neglect air resistance, determine how fast the balls would be traveling after 1.5 seconds. And I give you the equation. The height is negative 16 t squared plus 144, and this is in feet, and time is in seconds. How fast? That would be velocity, which is the derivative of the position graph, so we need h prime of t, which will be the velocity, will be negative 32t plus 0. And after 1.5 seconds, 1.5 times negative 32 is negative 48, and this is the velocity, feet per second. Number 3. Use calculus to determine this or explain why it doesn't exist. So, we have the limit as h approaches 0 of x squared over 1 minus e to the x. As h goes to 0, we have 0, the numerator going to 0, and the denominator going to, e to the 0 is 1, 1 minus 1, going to 0. So we can do L'Hopital's rule, and we'll have the limit as h approaches 0 of 2x, don't do the quotient rule in L'Hopital's rule, over derivative of 1 is 0, and minus e to the x derivative is minus e to the x. Now as h goes to 0, the numerator will go to 0, and e to the minus e to the 0, e to the 0 would be 1, so we get 0 over minus 1, which is 0. Number 3. Differentiate this. Well, this is a quotient rule. So it's a prime b minus b prime a over b squared. A is the numerator, so derivative of 5x minus 9 is 5 times the denominator, 2x plus e to the 2x, times b, so that's a prime times b, minus the derivative of the denominator. So the derivative of 2x is 2, plus the derivative of e to the x has chain rule in it. It'll be e to the 2x times the derivative of the inside, which is 2, times the numerator, over the denominator, squared. Number 5. Find the derivative of this. Tangent of x cosine of 2x. This is a product, so the derivative, I'm going to have to do a prime b plus b prime a. Derivative of tangent is secant squared x times b cosine 2x plus the derivative of b, derivative of cosine 2x, which chain rule here, so 2, derivative of the 2x is 2, times derivative of cosine is negative sine, leaving the inside alone, and times the first. Six. Find the slope at x equals 3. So we have f of x equals the square root, which is something to the 1/2 of x third minus 2. So f prime is going to be derivative of the inside. So derivative of this is 3x squared. Derivative of minus 2 is gone, 0. Times the derivative of the bigger picture, which is going to be half down, 1/2 times, leave the stuff alone inside, to 1 less power. And we're supposed to figure out this at 3, the slope. So this would be 27 times 1/2, 27 minus 2 to the minus 1/2. See, that would be 25, and this belongs to the denominator and square root, so this would be the 27 over 2, and this would be 1 over the square root of 25, which is 5, and so it's 27 tenths, or 0.27, 2.7. Okay. Next one. Implicit differentiation. So we have ln y minus sine of x squared plus y squared equals 3 halves. Derivative of ln y, since we're doing this with respect to x, we're going to have a dy dx, but the derivative of ln of something is 1 over the something. That's the derivative of the inside, dy dx, minus the derivative of sine. Well, we've got to do the derivative of the inside, and then times the bigger picture, the derivative of the sine. So the derivative of the inside, derivative of x squared is 2x, plus the derivative of y squared is 2y, but that's y, so we have to go dy dx. That's the derivative of the inside. Now the derivative of the bigger picture, sine of something is, when the sine is cosine, we leave the something alone, equals, and the derivative of 3 halves is 0. Okay. Number 8. Sand is falling off a conveyor belt and building a conical pile. Height is equal to the radius. What is the rate of change of the radius when the radius is 3? And sand is falling at a rate of so many cubic meters per hour. Okay, so we need to relate the volume, because this is cubic meters per hour, so that's dV dt, to the radius. And the height and radius are equal. So the volume is 1/3 pi r squared times h, but the radius and height are the same, so times r. H and r are the same, so this is 1/3 pi r cubed. So taking derivative with respect to time, we get dV dt equals 3 times 1/3 is 1 pi r squared. That's the derivative of r, dr dt, that we're taking with respect to time. Our dV is 0.45 cubic meters. Meters cubed per hour. It's really slow. Equals pi r. Now we can use a specific time. Oh, and they said when the radius is 3 meters, r squared dr dt. So this will be, what is the rate of change in the radius? Rate of change in the radius. So this is what we're looking for. So we're going to have 0.45, going to have meters cubed divided by meters squared, so that's just going to leave meters per hour, which is a good rate thing, divided by 9 pi. So let's see, 9 would go into this and make it 0.05, so we get 0.05 divided by pi. 0.05 divided by pi. I'm getting 0.0159 meters per hour. Not growing very fast. Let's just make sure I didn't do any arithmetic wrong there. 0.45 divided by parentheses 9 pi. Pi times 9. Yeah, right answer. Okay, let's go to 9. Two numbers, x and y, multiply to be 10. Okay, so x times y equals 10. And they always multiply to be 10. Let s be the sum of their squares. S equals the sum of the two numbers, so that would be x squared plus y squared. Find the pair of numbers x and y that minimize the sum. Well, I got two variables here, and the dependent variable and two independent. So I need to solve for one of these. So I'm going to use this. Let's just solve for x. So it would be 10 divided by y is x. And most of you would have probably done it the other way, but that's okay. So s would equal 10 over y squared plus y squared. If you had solved the other way, it would be 10 over x squared plus x squared. Anyway, so I've got 100 and over y squared, so that's y to the minus 2 plus y squared is the sum. So s prime is going to be negative 200 y to the negative 3 plus 2y. So if I set this equal to 0 to maximize, I'm going to have 2y equals 200 over y to the third. multiply both sides by y to the third, and I get 200 equals y to the fourth times 2, divide by 2. And then if I take both sides to the 1/4 power to get rid of the 4, I get y equals plus or minus, and 100 to the 0.25 is 3.16, and so y is either 3.16 or negative 3.16. If y was 3.16, x would be 10 divided by 3.16. So there's one pair of numbers. The other would be negative of 10 over 3.16. And that would minimize the sum. And you notice if you multiply these two, you get 10. Multiply these two, you get 10. Multiply to be 10. And that squared plus that squared would be a sum, and that squared plus that squared would be the same sum, because those squared give you. So those would be the minimum sums. Okay? And you could also type it in here, just to show you clear. After I've got it to one variable here, I'll use x instead of y. X and y are interchangeable, so I have 10 divided by x, that whole quantity, squared, plus x squared, and zoom 6, zoom 4. I don't know if you're seeing anything here. 10 divided by x, quantity squared plus y squared. Oh, probably too high. So let's make y max be like 30, because they multiply to be 10, so I'll make it 20. Oh, the sum of the squares is even higher. Window 200. There we go. We get the minimums are, so I can calculate the minimum. I'll say it's somewhere between 1 and 4. And my guess is 3. And it says 3.16227, whatever. Okay. All right. 9. 10. Looks like there's a lot to number 10, so let me get this paper, because I got all these bullets on it, number 10. So first thing it says to do is to find the first derivative and the second derivative. There's room here to do that, so I'll still get that here. So derivative of f prime of x would be 2 times a quarter is a half. And this is 8x to the minus 1, so it'd be minus 8x to the minus 2. That's the first derivative. And the second derivative would be 0.5. And so this is x to the minus 2, so it'd be plus 16x to the minus 3. Okay. Determine local maxima and minima. So we set the first derivative equal to 0. So we have 0.5x equals 8 over x squared. Multiply both sides by x squared, and I get 0.5x cubed equals 8. Divide by 0.5, and I get x to the third equals 16. So x equals the cube root of 16. And now how do I determine whether that's a max or minimum? I plug that into my second derivative and decide whether it's positive or negative. Well, the cube root of 16 cubed is 16. 16 divided by 16 is 1, plus 0.5 is 1.5. So f double prime of the cube root of 16 is 1.5, so it's positive, so it's concave up, so this must be a minimum. And I should find the points, so now I have to put this back in my original problem. So it would be the cube root of 16, comma, and then putting that into the original equation, it would be, let's just do that. I think I got the original equation in here. No, I got the, no, I have the original equation. Oh, this is from a different problem. So here, we got 0.25 x squared I should have cleared this first. Plus 8 divided by x. That's the original function, and I need to plug in the cube root. So that's 16 to the 1/3 power. Okay. Need to plug that into the function, and I get 4.7622. So there's the minimum point, and there is no maximum point because that was the only value that this was equal to 0. And let's just check that by looking at the graph. Zoom 6. So there's a local minimum. This just goes down like this, and so it's never going to have a max. Both of these keep going up, so there's a min, there is no max. Show how to use calculus to find any inflection points and determine these points. And so inflection points would be this equal to 0, so we'd have 0.5 equal to negative 16 over x to the third. So multiplying both sides by x to the third, I have 0.5 x to the third equals negative 16. Divide by 0.5, and I get x to the third equals negative 32. So x will equal the cube root of negative 32 for the inflection point. And let's see what that is. Negative 32, and I need the negative also. So insert parenthesis all the way over to close parenthesis to the 1/3. If you do it on older calculators, you have to put that in parentheses. And we get negative 3.7174. And I'm supposed to find the point. So I got to put that into the original equation. And so second table, and I'm putting in parenthesis negative 32, close parenthesis, to the 1 divided by 3. Oop, put the parenthesis there since it's in the exponent. Enter, and I get 0. So let's take a look at this graph again. Does it look like it's curved up, and then at 0 it starts curving down, and it happens at negative 3.147? Yep, and 0, so right on the x-axis there. So this is the inflection point. Okay. Determine the intervals where f is increasing and decreasing. Show how calculus can give you this information. So, the derivative, we just found out here. Let's go over here. I was going to turn it over, but the derivative is telling us the minimum. And so, that's at this value, which is, let's see, cube root of 16. 16 to the 1 divided by 3. 0.51. Oh, 2.52, roughly. So, we want to go above this to see if the slope is positive or negative, and below this to see if the slope is positive or negative. We also have a vertical asymptote at 0. So we're going to have to check the slopes. I'm looking at the graph and doing a sign chart. I have to find the slope at 0, and in between 0 and 2.52, and up here and down here. So I'm looking for what f prime is, the slope is, below 0. So if I put a negative number, that squared would still be positive, so I'd have a negative minus a negative. So it would be negative here, so it's decreasing. Between 0 and 2, like at 1, this would be a half minus 8, which is negative, so it's decreasing again. And then above this, we put in something like 3 or 4. 4 times a half would be 2, and 8 divided by 4 squared, 16, is a half, so 2 minus a half is positive. So it's decreasing below 0, decreasing between 0 and 2, and increasing beyond. F, and I did it for f prime of minus 1 is less than 0. F prime of 1 was less than 0. And f prime of 4 was greater than 0. So that's the calculus for whether it's increasing or decreasing. Again, you could just look at your calculator and see that, but I want you to show me the calculus that confirms that. Okay, so then determine the intervals where the function is concaved up or down. Show how calculus can give you this information. So we have, again, some critical places. So I'm going to look at the second derivative, and if that's 0, and we have a vertical asymptote at 0, so we're going to have to check concavity below it and concavity above that place, plus on either side of the inflection point, which was at negative 3.147. 174. So I want to check f double prime below that. And looking back here, that'd be a half. Minus 4 cubed is minus, so this would be 16 over 64. So 0.5 plus 16 divided by negative 4 I decided to put in, parenthesis, negative 4, close parenthesis, to the third. And that comes out to be 0.25 or positive. So it's concave up below this inflection point. Now between here and here, we can try maybe, this is 0, we can try maybe minus 1. So what's f double prime of minus 1? I think we could probably do that in our head. Minus 1 cubed is minus 1. So 16 divided by minus 1 is negative 16 plus 0.5 is negative 15.5. So it's concave down. It's negative and concave down. Now above here, we need to check. So let's put in 1. If I put in 1, 0.5 plus 16 over 1 is 16.5. F double prime of 1 is 16.5. It's positive, so it's concave up on all of this. Now let's check that with our graph. Concaved up over here, concave up until someplace in here, then it's concave down. So that's how to do that. The second derivative test for concavity. Okay, and finally, determine places where f is not differentiable. Well, we just said it's got a vertical asymptote, so it's not differentiable. T-I-A-B-L-E at x equals 0. Can't divide by 0, so vertical asymptote. Okay? All right. Back page. A ladder is leaning against the wall. There's a picture of the ladder. It is 5 meters in length. So the ladder's 5 meters. The bottom is being pulled away from the wall at 2 meters per minute. How fast is the top sliding down the wall when we're 3 meters away? So this is something that's changing. We can't use any value there. We want to know how fast this is changing, which is y. And we know that this is changing, so we're going to put an x there. And now what's the relationship between y and x? Well, x squared plus y squared equals 5 squared. Right triangle. Not using the 3, not using the 2, because this is the derivative, and we haven't done that yet. And this is only at one instant. It's not something that's fixed like the 5 is. So we can use the 5, but not the 3. So the derivative here with respect to time, so that'll be 2x dx dt plus 2y dy dt equals, the derivative of 5 is 0. And dx dt is what we have. And x, and we're supposed to do this when x is 3. We have the derivative now, so we can do this. And if this is 3, we need to know y at that point. So, we're using Pythagorean theorem again. 3 squared plus what squared is 5 squared. So 3 squared is 9, subtract it from 25, y squared is 16, so y must be 4 or negative 4. Negative 4 doesn't make sense, so we're using 4 in for the y, and we're going to find out how fast it's slipping down the wall, so we get 3 times 2 is 6, times 2, 12, equals 2y, plus 2y dy dt equals 0. So subtract 12 and divide by 2y. And so I get dy dt equals minus 12 divided by 2 times 4 is 8. And so we get negative 12 eighths, or negative 3 halves meters per minute. And it's negative because y is getting smaller instead of bigger. So that's the correct sign for that. Okay. And finally, number 12. We have to draw a graph. Probably should use a pencil on this because I might have to erase it. It's defined on the interval from -4 to 6. Has 2 points where the first derivative is 0. So it has to have slope of 0 twice. Has a y-intercept of 0, 3, so that one we can put on. And then at least one x-intercept at 4, 0. Now why it says at least one would be because it could just bounce, and that would be a double intercept, or bounce from the bottom, or if it passes through, that would be a single. It could be a triple if it comes up, goes flat, and then goes up again. So we've got, it goes here, at least bound, it hesitates or do something at 4. The second derivative is positive from -4 to 1. So for this whole interval, the second derivative is positive. So it's got to be concave up. And then negative from 1 to 5. So it's got to be concave down. The first derivative is positive on the interval from -2 to 2. I'll put that down here. So for this interval, it has to be increasing. Yeah, looking at the computer, it's hard to read what I wrote here. Concave up. Okay. That changes at that value. Okay. It's otherwise negative, so it's decreasing over here, and it's decreasing over here. The curve has an absolute maximum that is also a local maximum, but the absolute minimum is not a local minimum. Now, the only way to have an absolute maximum it can't be on the end if it's a local maximum also. And absolute minimum and not a local minimum would have to be on the end. Okay, so the function is decreasing here. So the minimum can't be on this side because it has to be at the end point. So the minimum must be over here, and it is decreasing, so it could go down, and 4 is there. So it could be the lowest place is right there, and it's got to be concave down. So that would be concave down and decreasing. And let's see what else we have to have. We have to be concave up. We have to hit here, but it's already concaved up. So I'm going to make it concaved up and then concave down. Concave down, going through that place, going through here, it's concaved up the rest of the way, but then it's increasing. Well, that's good. But right here, it changes to decreasing. Well, the only way I can change from increasing to decreasing and still be concaved up is to have a cusp. And so this would be my absolute maximum and also my local maximum. It's not differentiable there. And this would be the end. So it's decreasing, concaved up, increasing. Oh, it's supposed to be increasing in here. Uh-oh, I got something wrong here. Oh. So that can't be right. Going back to checking here. So I got a problem. Let's see here. Okay, so it's got to go through 0, 3, 1, 4. It's decreasing and concave down after that. Decreasing, so it's got to be going down and concave down. And then it's got to be increasing. Increasing and concave down. Increasing and concave down. So concave down, concave up, and no, at 4, but this was at 3. The first derivative, 2 points where the first derivative is 0 has a y-intercept of 3. The second derivative is positive. Okay, the first derivative is positive from -2 to 2. -2 to 2, the first derivative is positive. So it's increasing and decreasing everywhere else. So it's got to be this way, and then it's still decreasing, and it is concave down. So concave down and still concave down, decreasing. Now it's supposed to be increasing after that. When's the concavity change here? Second derivative is positive on 1 to 4, so it changes concavity at 1. So it's concave down, it's decreasing, concave down, and then it's still increasing, but it's concave down, so I'm going to have a cusp there. And then it's concave up, so it's going to have to come up and then come down to concave up to concave down. So it's going to have a cusp there. So concave down all this time and decreasing. Then it's concave down still here, but increasing, so it's going to have a cusp there. And at 1, it changes to concave up, so it has to go max and then come down, and it's got to be increasing. So this is increasing, and concaved up, so it's got to come up and then come down. So this would be increasing, concaved up, still concaved up, and decreasing, and concaved up. And I've got something here. So there it is, goes up to here, and then comes down, and then concave down. That's a tricky one.